Welcome back. In the last video, we talked about evaluating functions using things that were not just numbers. And one of the applications where we will need to evaluate a function, not just evaluate a number, is for a thing called the difference quotient. I'm going to kind of skip over what is the difference quotient, what does it represent, and all of that, because this is really a topic from calculus. So for those of you who are going on to calculus in the future, you will see the difference quotient there, and there it will be explained as to what is the purpose of the difference quotient, why do we care about it. For us here in Math 12, in pre-calculus, all we care about is being able to simplify a difference quotient. So all we need to know about it is that the difference quotient for a function is found by taking this expression, f of x plus h minus f of x, all divided by h, and then simplifying it. And what we mean by simplify is to get it to such a point where the h that we have in the denominator originally gets canceled out. And once we can get to the point where that h is canceled, then you've simplified your difference quotient as much as possible. And for the examples we're going to see in this class, you will always be able to do that. You'll always be able to do something algebraic to get it to the point where the h in the denominator cancels. This is not the same thing as saying that every single h is going to go away. There very well will be some h's left over. It's just the h that we originally had in the denominator, that particular h got canceled, and when we get to that point, we'll be in simplest terms for a difference quotient. There is one little thing to note here, and this is a little exception to how we live our lives usually. Up till now, I've said anytime you see a fraction, if there's roots, you need to make sure that you rationalize the denominator. This is the one exception where we will not be rationalizing our denominator. We're going to see an example where to have a difference quotient in simplest terms, that will mean having roots in the denominator, and there's no way around that. So that is the one exception. So if you're looking at a difference quotient and it's a function involving a root, your final answer may not have a rationalized denominator, and that's fine. So we'll see that in just a moment. But first, we're going to start with a nicer one. So here we've got a polynomial function, and we want to find our difference quotient for it and to simplify it. Probably a good idea before we do the full difference quotient is to calculate what f of x plus h is. And that's because, of course, our difference quotient involves f of x plus h's and f of x's. F of x, we already know what that is. We were given that. So once we know what f of x plus h is, then we'll be having an easier job of simplifying that difference quotient. So to find f of x plus h, same thing as before, I'm replacing all of my x's in my original function with x plus h. And then I'm going to just expand and simplify. So we're multiplying together x plus h times itself. I've already carried the 2 through that second bracket, and now I'm just multiplying the 3 on in so that I've got 3x squared plus 6xh plus 3h squared. Okay, so I've got my difference quotient ready to go. I just have to put it together. I already know what f of x is. I now have figured out what f of x plus h is. So let's get started. Our difference quotient is f of x plus h minus f of x all over h. And I'm going to write that h in green throughout so that I can keep track of which h I'm supposed to be getting rid of. Because remember, it's only the h that was in the denominator that needs to be canceled, not all the other h's that are out there. So from f of x plus h, I already know what that is. That's 3x squared, 6xh, 3h squared, 2x, 2h, and 1. And for subtracting f of x, here's where I'm going to again be a little bit careful, since I want to make sure that I subtract all of f of x when I'm subtracting f of x, I'll do so in brackets to remind myself that I'm not just going to be subtracting the first term, I'm subtracting the entirety of f of x. So I want to subtract the 3x squared and also the 2x and also the plus 1. All of those need to be subtracted. And all of this is over my denominator of h. And as I'm carrying out my subtraction, I can see a bunch of things are going to go away. I have the 3x squared minus the 3x squared. Those will be gone. I'll have the 2x minus the 2x. That will be gone. And the 1 minus the 1. That will be gone. So the only thing left would be the 6xh, the 3h squared, and the 2h. And here I notice that I could factor an h out of everybody in the top. And when I do that, I can see that I can now cancel the h that was on the top with the h that I wanted to get rid of, the one that was in the denominator. And so that means for my difference quotient, it simplifies to give me just 6x plus 3h plus 2. And there we go. That's my simplified difference quotient. So again, the idea for getting your difference quotient, we start off with first figure out what f of x plus h is. Take a minute there to simplify that. Then for your difference quotient, the f of x plus h that you just found, minus your original function f of x, all divided by h. Then we just do some sort of algebra to simplify, and then at some point we'll be able to cancel our h. The only thing that's different from one question to the next is what you'll need to do in the middle steps, what kind of simplifying you'll need to do to get to the point where the h's will be able to cancel. But for this example, we canceled the h's out, and it was easy enough to do since it was a polynomial function. We just basically had to expand and factor out an h, and then we were finished. There's two other kinds of functions that we're going to see. One of them is a rational function, and then the other one is a radical function, one involving roots. And they both have their little quirks as to what we should be doing to simplify those. Okay, so let's do this next one. Our function g of x, this is 2 over 3 times x plus 1. So first thing I'm going to do, I'm going to figure out what g of x plus h is. And again, I need to be careful about the substituting in with brackets. So a common mistake that I'll see with this, common mistake number one will be people who just put an h at the very end, which that is extremely wrong. Remember, f of x plus h or g of x plus h, we don't find that just by putting an h at the end. We have to replace all of the x's with x plus h's. So, too bad for that. The other common mistake that I'll frequently see is that when people are finding g of x plus h, they will just put in x and then put an h next to the x and then stop there. And this would also be wrong. The reason it's wrong is because, remember, when we're substituting and we're replacing our x with our x with x plus h, we need to do so in brackets. In the original function, 3 was being multiplied against our input x, which means in our g of x plus h, 3 needs to be multiplied against that input x plus h. So it really should be 2 over 3 times x plus h in brackets plus 1. Or if we were simplifying it, 2 over 3x plus 3h plus 1. Okay, so now we've got our g of x plus h figured out, so let's do our difference quotient. And that is g of x plus h minus g of x all over h. And g of x plus h, we've got that already figured out. That's 2 over 3x plus 3h plus 1. And g of x, that's 2 over 3x plus 1. And in our denominator, we have got h. So if you're having a flashback to section 1.6, when we were talking about compound fractions, when you have fractions inside of fractions, yet again, we've got that going on here. We have the difference quotient itself as a fraction, but in our numerator, we've got fractions. And the easiest way for us to get rid of fractions inside of fractions is for us to say for the little fractions, what would be the common denominator? And once we decide what the common denominator is, we'll multiply the top of our fraction by it and also the bottom of our fraction by it. So our common denominator would be 3x plus 3h plus 1 times a 3x plus 1. So that's what I'm going to multiply top and bottom of my fraction. 3x plus 3h plus 1 times 3x plus 1 on the top. And I'll do the same thing on the bottom. So for the bottom part of things, and I'll do that first, I'm going to just leave it as h times the one bracket times the other bracket. I'm not going to bother to expand things. And part of the reason why I'm not going to bother to expand things is because, remember, my ultimate goal is for me to cancel this h out. So if I multiplied everybody together, I would be mixing that h in with all the other terms, which is making it harder for me to later on get rid of that h. I want that h to already be kind of separate so that I can do my canceling later on. For the numerator, when I multiply the first fraction by these two brackets, the 3x plus 3h's plus 1's will cancel, leaving just the 2 times the 3x plus 1. And for my second fraction, the 3x plus 1's cancel, leaving just 2 times the 3x plus 3h plus 1. Okay, so we're most of the way there, believe it or not. There's only a little bit of extra work for us to do, which is going to essentially come down to simplifying the top, and then we'll be able to cancel. So the bottom, again, I'm going to leave that as it currently stands. I'm not going to do any simplifying here, expanding on the bottom. It's going to be left as h times 3x plus 3h plus 1, 3x plus 1. And on the top, I'm going to expand, and I have to be a little careful when I expand. So for the very first one, on the left side, we have 2 times 3x plus 1, which when I expand it gives me 6x plus 2. Where I need to be careful is for this second bracket. Keep in mind that when we're multiplying the 2 on into the bracket, it's not really 2, it's negative 2. So we'll have a minus 6x, a minus 6h, and a minus 2. And now we're almost finished because we can see here in the numerator that the 6x and the minus 6x will cancel. The 2 and the minus 2 will cancel. So what are we going to be left with? Well, we'll just have minus 6h on the top, and on the bottom, h times 3x plus 3h plus 1 times 3x plus 1. And now I can see my path to the end. I can cancel my h's, and that will leave me with my simplified difference quotient, negative 6 all over 3x plus 3h plus 1 times 3x plus 1. One thing that I know people usually have a concern about is the fact that in our denominator there is an h, and people get worried about the fact that we didn't get rid of every single h in this question. And again, the reminder is that we don't have to get rid of every h, we just have to get rid of the h that was originally in the denominator, and that was the little green h that I've had all along. That h I did manage to get rid of. The fact that I've got other h's that are still there is not a problem. I just needed to get to the point where the h in the denominator got canceled, and I did it. So I can now feel pretty happy about what we've done here. Okay, so last one to work on. Whoop, Last one to work on is this radical function. We've got this p of x being root of 5x plus 2, and we want to find and simplify the difference quotient for that. So again, we're going to find p of x plus h by replacing the x with x plus h, and again, remembering to replace them in brackets. If we just write 5x plus h plus 2, that's not quite right. The 5 needs to multiply against my entire input, and my entire input is the x and also the plus h. So my p of x plus h is really root of 5x plus 5h plus 2. Okay, so if I were to start off with my difference quotient, I would say that that would be p of x plus h minus p of x all over h. So I would have root of 5x plus 5h plus 2 minus root of 5x plus 2 all over h. For this one, this is the one where it's a little bit of a twist as to what we'd be doing. It's something that we've not needed to do before. For this, right now, there's not really anything you could do with these individually. You can't combine these roots together. Remember that we don't have any radical properties for adding or subtracting roots. We have them for multiplying roots together or dividing one root by another, but not for subtracting one root from another. Sorry, unfortunately. The one thing that we have seen that we could use was a sort of a technique that we did to rationalize a denominator in the past. Here we're going to do it to rationalize our numerator. And you might be asking yourself, why do you need to rationalize your numerator? And the answer is, for these kinds of functions, radical functions, this is the little secret tip that you'll need. That if we rationalize our numerator, if we get rid of the roots in our numerator, we'll be able to get at the h that we have in our numerator and hopefully cancel it with the one that we have in our denominator. So just hang out and watch the fun unfold. I'm going to do the same thing I've done before using the conjugate. I'm going to multiply top and bottom by my conjugate. In this case, it's 5x plus 5h plus 2 square rooted plus root of 5x plus 2. And I'm going to kind of do the same thing that I did before, where on the bottom, I'm not going to bother expanding things. So for my denominator, I'm going to write it just simply as h times these two roots added together. So for my denominator, I'm just going to write it as h times first root plus the second one. And the reason is same as before why I'm not going to bother expanding things, and that's because eventually I want to cancel that h that's in the denominator, and if I start expanding things and combining the h's with the two individual terms, that's just going to mean it's something else for me to undo later on. So I'll leave the h there for now. And in the top, we know that when you multiply something by its conjugate, you get the first thing squared minus the second thing squared. And by doing that, that's going to get rid of our roots. So instead of having root of 5x plus 5h plus 2, we're going to just have 5x plus 5h plus 2. And instead of root of 5x plus 2, we're just going to have 5x plus 2. So let's do that on the next slide. You'll notice that I'm keeping things in brackets for now, and that's because, again, I have to remind myself that in the numerator, I had that one first square root minus that second square root. Now that we've gotten rid of the square roots, what was on the inside, the first thing, from that I'm going to subtract the entire inside of the second thing. I'm subtracting the 5x and also subtracting the 2. So that means a lot of things are going to go away here. I'm going to have, same as before, the 5x and the 5x, those will cancel each other out just nicely. I'll have a 2 minus a 2, those will cancel each other out, which means that in the numerator, all I'll have left is 5h, and in the denominator, I'll have h times my 2 roots. And you can kind of see where I'm going to go next with this. I'm going to cancel my h's, and then once I've done that, I will be finished. I have an h in the numerator that will cancel with the h in the denominator. And there we go. We've got our difference quotient simplified. I'm just going to write that out. 5x plus 5h plus 2, and then plus root of 5x plus 2. One caution here, and this is sort of to remind ourselves that this is the one exception in the course where we kind of have no choice but to have to leave things with an unrationalized denominator. For almost everything else in this course, if we saw roots in our denominator, we would have to rationalize them. The reason why we're leaving our roots in the denominator here and not rationalizing them is because if you decided that you wanted to rationalize this denominator, what will happen will be, so if I multiplied top and bottom by the conjugate, and then simplified and cleaned things up, it would actually take me right back to the very first step. In other words, rationalizing the denominator would undo all the work that I did, put the h back in the denominator, and so in other words, there's no point here for this question to rationalize our denominator. In fact, in order for us to simplify our difference quotient, we have to leave our denominator in that form. We really have no other way around it.